Now that you've learned about capacitors, there's some fun problems that you can solve by considering how the charges redistribute from one of the capacitor plates to other capacitor plates when the capacitors are connected in different configurations. So let's have a look at an example problem now.
So the problem is you have two identical capacitors which are both charged to a potential of 120 volts. Their positive terminals are then joined together and their negative terminals are connected across the 120 volt battery. Calculate the final voltage across each capacitor. So to start this, let's draw a little diagram. So here's C1. Now they've got the same capacitance, but it'll be useful to be able to distinguish our capacitors. And here's C2. And initially they're joined with their positive terminals together. So here we've got plus Q1, and let's call it Q1 dash to indicate the initial charge Q1 that it had once it was charged by itself. And here's the negative plate. And then here we've got plus Q2 dash, and here's minus Q2 dash. And then we connect our battery. So let's draw it connected with the battery down here. So here's the positive terminal of our battery. So after the charges have redistributed, the battery will supply some charge, and we'll end up with this is Q1 plus Q1, and here we'll have minus Q1, and this is capacitor 2. We'll have minus Q2 on this side and plus Q2 on that side. So what you can hopefully see from these diagrams is if we consider this part of the circuit here within this box, it's not connected to the outside, so the charge inside these boxes can't have changed. So we can write down that Q1 dash, meaning the initial charge on Q1, plus Q2 dash is equal to minus Q1, where without the dash is the final charge, plus Q2. Now we can work out what these initial charges are because we've got our capacitor equation, C is equal to Q over V, and we were told that these were initially charged to a potential of 120 volts. So that tells us that Q1 dash is going to just be equal to CV, and Q2 dash is going to be the same thing because they're the same capacitors. The capacitances are the same, C1 equals C2 equals C. So we can say, well, this thing then is equal to 2CV, and that is equal to minus Q1. So afterwards, the Q1 is going to be C1, which is just C times V1, and that's negative, plus Q2, which we can see Q2 will be C times V, so C times V2, where V2 is the voltage drop across this one, and V1 is the voltage drop across this one. So you can see our capacitances cancel out, and we've got an equation 2V is equal to negative V1 plus V2. Now, the other equation we can write for voltage, considering this final arrangement here, is the battery supplying a voltage V, which we have a potential difference of V1 across this capacitor and V2 across this capacitor. So we know that V must equal V1 plus V2. So then what we can do is sum these equations together. So let's call this one 1 and this one 2. And then we've got 1 plus 2. And so this tells us that 3V is equal to, the V1s will cancel and the 2Vs will add, 2V2. So that tells us that V2 is equal to 3 over 2V, which is equal to 3 over 2 times 120. So that is equal to 180 volts. And V1, we can just rearrange 2, which tells us this is equal to V minus V2. So that is equal to 120 minus 180. So that is equal to minus 60 volts. So now we've found the potential difference across each of those capacitors.